Hello everyone. Last class we discussed BEE fourth unit topics, electrical machines. In that we have done the generation of rotating magnetic field and the construction and working of three-phase induction motor. Depending upon rotor, we have two types of induction motors. One is squirrel cage, another one is slip ring. Now today we will see significance of torque slip characteristics and losses of components and efficiency. Before going to deal with this topic, we should know what is meant by slip, what is meant by torque. Try to observe slip. Generally, the slip speed is equal, we can write ns minus nr. Ns is a synchronous speed and nr is a relative speed. For example, if I take the synchronous speed is 1500 rpm and the relative speed of the motor is 1460. The slip speed is equal to around 440 rpm. If I take slip, we can directly write ns minus nr by ns. It is equal to, we know, ns minus nr value 40 by 1500. This is equal to the slip of the induction motor. And coming to the torque, in case of electrical motor, the torque we can define as power into omega s. Here power we all know, voltage into current, and then power factor by omega s we will know 2 pi ns by 60. It is an angular velocity. In this torque we have three major things. First one is at the starting we called as starting torque, and then at the position where we'll get the maximum torque, and the last one is the full load torque. We will go through with these three torques. One is starting torque, maximum torque and full load torque with respect to slip, how the torque will varies, and we will deal with the power losses also. Now observe here rotor speed, and slip. If you can observe, we know omega angular speed it is equal to 2 pi ns by 60, and we can say that if there are p by 2 pole pairs, we can directly write omega is equal to 2 pi ns by 60 p by 2. As we know, angular frequency is equal to omega is equal to 2 pi mnf. Then we can equate this equation 1 and equation 2. Then you will get the f is equal p ns by 120. If you observe here, what is ns? Ns is equal, can I rewrite 120 f by p? For example, in our domestic, you will get the frequency of 50 Hz and the number of poles I am assuming here 2. Then you will get 3000 rpm. It is nothing but a synchronous speed. Now here we can observe the slip speed. I already said slip speed is equal to ns minus nr. Coming to the slip is equal, s is equal to ns minus nr by ns. Try to observe this. We can rewrite 1 minus nr by ns. It is equal to nr by ns is equal to 1 minus ns. If you want to determine relative speed, if they given the slip, we can write ns into 1 minus s slip. It is used to determine the relative speed. We already discussed at the starting the slip is equal to 1. How can we determine? We know s is equal to ns minus nr by ns. We know at starting ns starting nr relative speed is equal to 0. Then if you substitute nr is equal to 0, you will get slip value 1. ns by ns will get cancelled out and you will get at starting slip is equal to 1. Try to remember this. At the full load or at the high speed, S is equal to 0. Ns is equal to nr. The synchronous speed is equal to relative speed. Thus, in that case, S is equal to 0. Now, here observe the effect of slip on the rotor parameters. If the slip is varies, how it will affect the rotor parameters? Effect on frequency of rotor voltage and current. Try to observe this point. Fr is equal to, we can directly write ns minus nr. We know F is directly proportional to the ns from the above equation. Now from dividing equation 1 by equation 2, you will get Fr by F is equal to ns minus nr by ns. It is equal to S. It is nothing but a slip. Fr is nothing but a rotor frequency. F is a stator frequency. That is Fr is equal to N in S into F. For example, rotor frequency is equal to, if I am assuming slip value 0.04 and the frequency is equal to 50 Hz. If you multiply these two, you will get 2 frequency, 2 Hz. That value is equal to 2 Hz. The stator frequency, if you given 50 Hz, how much rotor frequency you will get? 2 Hz. It is the effect. And then effect on magnitude and rotor induced EMF. Previously we discussed the frequency, how it will affect on the rotor. Now we will discuss effect and magnitude of rotor induced EMF. Similar like rotor frequency, how it is Fr is equal to S into Fs. Similar way, in this case of also rotor frequency is equal to S times of supply voltage of E2. Observe here multiplication of S. Now observe over here effect on rotor resistance and the reactance. Now observe this. We know resonance frequency. Sorry, we know secondary rotor reactance is equal to 2 pi Fr into L2. That Fr we know, Fr we can substitute to SF. That value equal to S into X2. It means the rotor reactance is equal to slip into the rotor reactance X2. Coming to the effect on rotor current and rotor power factor. Now observe over here. We know Z is equal to impedance is equal to R2 plus JX2. That we can substitute R2 plus X2 whole square. At standstill, we know at standstill S is equal to, we can substitute 1. Then you will get I2 is equal to just E2 by Z2. That is a vector form. Then E2 is E2 by under root R square plus X2 whole square. Coming to power factor, we know R by Z2 from the impedance triangle, that R2 by under root R2 plus X2 square. These are at standstill S is equal to 1. Under running condition, if you observe, rotor voltage is equal to S into E2 secondary voltage, and the rotor resistance is equal to R2, and the rotor winding reactance per phase is equal to S times of X2. If I substitute all these values in Z to R, you will get this equation. And we know the current per phase is equal to I to R is equal to E to R by Z to R. That is nothing but a S E2 by under root R2 square plus SX2 whole square. And that is equal to, and we can write the power factor is equal to R2 by Z to R is equal to R2 by under root R2 square plus SX2 whole square from the impedance triangle. Now we will draw equivalent circuit diagram per phase of rotor. In case of standstill, simply S is equal, we can take 1, and then here you will get E2, I2, R2, X2. There is no S value because S is considered as a 1. But in this case of under running condition, the rotor voltage is equal secondary voltage and multiplication of S and I 2R is equal to R 2R is equal to R2 and X 2R is equal to S into X2. These are 5 per phase values. Now coming to the torque equation. Now our main topic is the torque slip characteristic. In this the torque equation of three-phase induction motor. Try to observe this. The torque is directly proportional to the flux and secondary current and the power factor. That flux is directly proportional to the secondary voltage and the current and power factor. We can directly write T is equal to K E to I2 by cos phi 2, and we derive the current from above equations. I2 is equal to, we know, E2 by Z2, E2 by under root R2 square plus X2 square. This is at starting torque. We already discussed we have three types of torque. One is starting torque, second one is maximum torque, and third one is full load torque. Now we are discussing starting torque. In the starting torque, I2 is equal to E2 by Z2 and cos phi 2 is equal to R2 by Z2, that R2 by R2 under root R2 square plus X2 square. We can substitute all these values. Finally, you got this equation. It is very, very important. We can directly write I starting is directly proportional to E2 square R2 by R2 square plus X2 square. In this there is no S because it stands still. S is equal to 1. The starting torque is directly proportional to the secondary voltage square and R2 by R2 square plus X2 square. Now coming to the condition for maximum starting torque. Try to observe this. We already discussed we have three types of torque: starting and condition for maximum starting torque. To get the maximum condition, we should differentiate with respect to R2 variable resistance, that is nothing but a load, that d by dr2 square k1 into R2 by R2 square plus k2 square, if equating to 0. After solving this, the condition is R2 should be, try to observe this, R2 should be equal to X2. Resistance is equal to reactance. At this condition, you will get maximum starting torque. Maximum starting torque. That value we can directly determine. E2 by 2 R2 square. Isn't it? If you substitute the R2 is X2 in the above equation, you will get this value. Now, the torque under the running condition, at this condition, we don't take S value as a 1. We have to take S value, certain value. Then we have to substitute voltage E2R is equal to SE2, I2R is equal to, we already derived this equation from the above equations, and the power factor is equal to R2 by under root R2 square plus SX2 square. The torque running under the condition is directly proportional to, observe this equation, is directly proportional to the running condition S E2 square R2 by under root R2 square S X2 whole square. Here the torque under running condition, to get the maximum running condition, the maximum torque under running condition, we should differentiate that equation and equating to 0. When you differentiate and equate it to 0, you will get R2 is equal to Sx2. At standstill, you got only R2 is equal to X2, where S is equal to 1. In the running condition, you will get R2 is equal to Sx2. Try to observe this true difference. And if you substitute the values in that equation, finally you will get this value. Torque maximum is equal to E2 square by 2x2. As of now, we discuss last one is full load torque and maximum torque. The relation between these two, the full load torque is equal SF E2 square R2 by R2 square plus SF X2 whole square, and the maximum torque is equal to E2 square x to x square. If you divide it by equation 1 with respect to equation 2, you will get this final relation 2asf and a square plus sf square, where a is equal to, we can write r2 by x2. It is the relation for it is relation for T full load to T maximum 2as by s square plus x square. Now coming to the relation for starting torque to maximum torque, simply we can substitute s is equal to 1. You will get 2a by 1 plus a square. It is the final result. The starting torque by maximum torque is equal to 2a by 1 plus a square. Before we observe where you will exist s value. Here there is no s value because s is equal to 1. We can substitute over there. After completion of basics, now we will go with the torque slip characteristics. In this, we have to take slip values from 1 to 0. It means from starting to running condition. Running condition. It means the starting, the relative speed is equal to 0 and the up to it is equal to synchronous speed. If you observe the torque equation, torque is equal 3 times by 2 pi ns by 60 into s e2 square r2 by r2 square plus s x2 whole square. You can simply write that value k into s e2 square r2 by r2 square plus s x2. If you observe the graph between torque and slip, this is the main important thing in your exams. You have to write this equation and draw this graph. It is a graph drawn between the torque and slip. Observe the slip values from 1 to 0. At the starting, the slip is equal to 1. At running, the slip near to the 0 0.2. It is the slip value. If you observe the speed, here they taken into unit values. The speed is increasing from 0 to 1 unit. In this case, in this graph, you can observe up to this region. So V2A we called as unstable region and O2A we called as stable region, and it is the operating region also. This in this it is B at this point B we called as starting torque, and the A point is called as a maximum torque, and here if you observe at any point in this it is called a running torque. It is also called as full load torque. Try to observe this graph. The graph is start from starting and increasing. If you observe this, the torque is here, from torque is increasing. Torque is increasing, the slip is decreasing. At the starting from here, we can directly say that at the low, at the high slip, the torque is inversely proportional. In this region, the torque is decreasing, slip also decreasing. Torque is directly proportional to slip. At the medium region also, the torque is directly proportional to slip. Try to observe this. At the starting, slip is inversely proportional to torque. At the high, at the maximum torque after the low slip, the torque is directly proportional to the slip. As we said that we can observe low slip region. Low slip region is nothing but a full load or running region. Full load or running region. At this case, the torque is equal to SE2 square R2 by R2 square plus SX2 square. If the S value is low, we can neglect this value. If you neglect this value, you will get S R2 by R2 square. It is simply we can cancel out this R2 R2. You will finally get only S. The torque is directly proportional to S at low slip. Try to observe this at low slip. At the medium slip, we can neglect this value R2 square compared to SX2. Then this S, this s square you will get cancelled. Finally, you will get 1 by s. At the medium slip, torque is inversely proportional to the slip. The third one is high slip region. In this high slip region, S value is high near to the 1. In that case also S is indirectly proportional to the slip, as we know, and we can take this is, and it is the final graph between torque versus slip. The machine can work as a generator, generator and motor and braking mode also. Braking mode. From slip from 0 to 1, it acts as a motor mode. After 0, you may get negative slip. It means the rotor rotates more than synchronous speed. It acts as a generator. If the slip is greater than the 1 value, it is called as a braking region. It is a complete torque slip characteristics of three-phase induction. Now we can conclude this topic. The main concept in this torque slip characteristic, at the high torque, high slip region, the torque is inversely proportional. When the torque increases, when the slip decreases, the torque will increases. In this region, the torque is directly proportional to the slip. When the torque is decreases, slip is decreases, torque is also decreases. Try to observe these 2 points. When the torque is decreases, slip is increases in the high slip region. In the low slip region, slip is decreases, torque is also decreases. In your exam, you have to draw these two graphs. Torque slip characteristics, you should draw these two diagrams. I hope all of you understood. Thank you.